we are discussing complex analysis. The total content is divided into 10 chapters. We already discussed chapter 1. Now we will discuss chapter 2. The topic is concept of functions, limit and continuity. This chapter contains 3 modules. Module 1, basic definitions, module 2, limit of a function, and module 3, continuity of a function. Now we discuss module 1, that is basic definitions. In this module, we first give some introductory definitions along with 2 important theorems in complex analysis named as Bolzano-Versus theorem and Jordan-Karp theorem. After this, we will introduce the concept of functions of complex variable, its classification as single valued function, multiple valued function, univalent function, etc. Then we will discuss the composition of 2 functions. At last, we will give some examples related to this module. So, this is our module 1, concept of functions, basic definitions. So, students are well known the definitions of limit and continuity for a function of real variable. In this chapter, we shall discuss the corresponding definitions for functions of a complex variable, its limit and continuity. So, first we give some definition. First is neighborhood of a point. Suppose C be the complex plane and Z0 be any point in the complex plane C. By a neighborhood of the point Z0, we mean all such points Z such that modulus Z minus Z0 is less than R, where R is some positive number. That is the set of all points lying in the disk having center at Z0 and radius R. If we exclude the point Z0 itself from this neighborhood, then it is called a deleted neighborhood of Z0, and we can write this by 0 less than mod Z minus Z0 less than R. So, now limit point. A point Z0 in C is called a limit point of a set S which is a subset of C if every deleted neighborhood of Z0 contains at least one point of S. A limit point may or may not belong to the set. As for example, all points on the circle mod Z equal to R are the limit points of the set mod Z less than R, which do not belong to the set. But all the points within the circle mod Z equal to R are also limit points of the set, and they must belong to the set mod Z less than R. Now we define what is called interior, exterior and boundary points. Suppose S be a subset of complex plane C. A point Z0 in S is called an interior point of S if there exists a neighborhood of Z0 contained entirely within the set S. A point Z0 is called an exterior point of the set S if there exists a neighborhood of Z0 which contains no point of S. A point Z0 is called a boundary point of a set S if every deleted neighborhood of Z0 contains at least one point of S and at least one point of the complement of S. The collection of all such boundary points of the set S is called the boundary of the set S. Now we define open set and closed set. A set S subset of C is called an open set if it consists only of interior points. The set S is called closed if all limit points of S belong to the set S, or if S has no limit point. If the set S is closed, obviously its complement set is open. So, there are sets which are neither open nor closed, and also there are sets which are both open and closed. As for example, the sets void set and the set itself C are both open and closed. The set A containing the elements Z such that 0 less than mod Z minus Z0 less or equal to R is neither open nor closed. The open disk mod Z less than 1 is an open set, whereas the closed disk mod Z less or equal to 1 is an example of closed set. Also we note that the intersection of a finite number of open sets is open, and the arbitrary union of open sets is also open. Now we define convex set. A set S subset of C is said to be convex if a line segment joining any pair of points of S lies in the set S. Mathematically, we can write 1 minus t into Z1 plus t Z2 belongs to S whenever Z1 Z2 belongs to S and t varies from closed interval 0 1. An open disk, half planes and rectangles are examples of convex sets, whereas the set C excluding the point Z equal to x, where x greater than 0 is not a convex set. So, now bounded, unbounded and compact set. A set S which is a subset of C is called bounded if there exists a positive number m such that mod Z is less or equal to m for all Z belongs to S. If no such number m can be found, then the set is called unbounded. The set S is called compact if it is both bounded and closed. So, now we define derived set, closure of a set and connected set. The set of all limit points of a set S is called the derived set of S and is denoted by S prime. The set S together with its derived set S prime is called closure of the set and is denoted by S bar or CLS. a set S is called connected if any two of its points can be joined by a polygon, all of whose points belong to the set. Now we define domain. A non-empty, open and connected set in C is called a domain, whereas if the boundary points are also included, then it is called a closed domain. It is to be noted that every neighborhood of a point in the complex plane is a domain. A domain together with some, none or all of its boundary points will be called as region. From this we can say that every domain is a region, but the converse may not be true. Now Jordan curve. The equation z equal to z of t equal to x of t plus I y of t, where x of t and y of t are real valued continuous function of the real variable t, and t lies in closed interval a b, determines a set of points in the complex plane which we call a continuous curve. The equation z equal to zt equal to xt plus iyt is called a simple curve if t1 not equal to t2 implies z of t1 is not equal to z of t2. The equation z equal to zt equal to xt plus iyt is called a simple closed curve if t1 less than t2 and z of t1 equal to z of t2 implies t1 is equal to a and t2 is equal to b. Simple curves are sometimes called Jordan curves. An example of a Jordan curve is a polygon consisting of a finite number of line segments joined end to end. Now we will mention an important theorem of bounded infinite sets, and the theorem is Bolzano-Weierstrass theorem, and it tells that if a set S subset of C is bounded and contains infinite number of points, then it has at least one limit point. Another theorem which is important in complex analysis named as Jordan curve theorem, and it tells that a Jordan curve divides the complex plane into regions, of which the curve itself is the common boundary. The region which is bounded by the curve is called the interior of the curve, whereas the other region is called the exterior of the curve. As for example, we can say that the circle mod z equal to 1 divides the complex plane into two domains. One is mod z less than 1, which is bounded, and another is the interior of the circle mod z equal to 1, and the other mod z greater than 1 is unbounded and is the exterior of the circle mod z equal to 1. So, just now we discussed two important theorem in complex analysis. One is Bolzano-Weierstrass theorem and another is Jordan curve theorem. For the proof of Bolzano-Versus theorem, please consult the book of S. Punnaswamy and H. Silverman. The title is Complex Variable with Applications. For the proof of Jordan curve theorem, please consult the book of M. Newman, Elements of the Topology of Plane of Points. Besides this, there are another important theorem in complex analysis named as Heine-Borel theorem. This theorem tells that every closed and bounded set is compact. Therefore, if S is a subset of the complex plane C, then the statements number 1, S is closed and bounded, number 2, S is compact, number 3, every infinite subset of S has a limit point in S, number 4, every convergent sequence in S has a subsequence which converges in S are equivalent. Now we will discuss the function of complex variable. So we now discuss the functions of a complex variable. Let S subset of the complex plane C. A symbol like Z which represents any one of elements of S is called a complex variable. Let S subset of C. By a function f from S to C, we mean a rule which assigns to each Z belongs to S a unique value f of Z belongs to C, and we write this by W equal to f of Z, where Z belongs to S. In this case, we say that f is a complex function of a complex variable Z. The variable Z is called the independent variable and W is called the dependent variable. It is customary to locate f of Z belongs to C in another complex plane which we call as W plane. S is called the domain of f and the set f of Z where Z belongs to S is called the range of f. Note that if S is a subset of the real line, we say that f is a complex function of a real variable. Every function f of Z can be written as fz equal to u of xy plus I v of xy, or we can write f equal to u plus iv. As for example, f of z equal to z square plus 1 if and only if f of z equal to x plus iy whole square plus 1, if and only if fz equal to x square minus y square plus 1 plus I to xy. Again, fz equal to z square plus 3z plus 2 if and only if fz equal to x square minus y square plus 3x plus 2 plus I into 2xy plus 3y. It is obvious that both u and v are real valued functions of two real variables x and y, and will be referred to as real and imaginary components of fz respectively. In case where the domain of definition is not specified, we take the largest possible set as the domain of f, on which f is well defined. For the function fz equal to 1 by z square plus 1, the domain of definition is the set S, which is equal to C excepted the value I and minus I, and for the function fz equal to argument z, the domain of definition is the set C excluding the point 0. If more than one value of w corresponds to each value of z, then we say that w is a multi-valued or multiple valued or many valued function of z. A multi-valued function can be considered as a collection of single valued functions, each member of which is called a branch of that function. So, obviously, every branch is a single valued function. It is customary to consider one particular branch as a principal branch. Now, example, we consider the function w equal to fz equal to 2z plus 3. Here, to each value of z, there corresponds only one value of w. Therefore, the function fz given by 2z plus 3 is a single valued function of z. Another example, if we consider the function w equal to fz is equal to z to the power half, then to each value of z there are two values of w. Therefore, fz equal to z to the power half is a multi-valued function of z. Similarly, if we take w equal to fz equal to z to the power 1 by third, then here also to each value of z there are three values of w, and therefore, the function fz equal to z to the power 1 by third is also a multi-valued function of z. Suppose that f is a complex function defined on a set S, which is a subset of C. If f z1 equal to f z2 implies z1 equal to z2 for all z1 z2 belongs to S, or equivalently we can write z1 not equal to z2 implies f of z1 not equal to f of z2 for all z1 z2 belongs to S, then we say that the function w equal to fz is 1 1. If the function w equal to fz defined on a set S is 1 1, then the function f is called univalent on S. Note that a function f is univalent at a point z0 if it is univalent in some neighborhood of z0. Suppose that f is a function from d1 into d2 is univalent and onto, then we can define an inverse function as z equal to f inverse of w if w equal to fz. It is obvious that the inverse function is also univalent on D2. Suppose we have a function f with domain D1 and another function g with domain D2. Suppose further that for every z in D1, fz belongs to D2. Then for every z in D1, the composition of f with g is the function gf defined by gf of z is equal to g of fz, where z belongs to D1. For instance, we assume that fz equal to 3z plus 2 and gz equal to z cube plus 1 defined on C. Then gf of z is equal to g of fz, and obviously it is equal to g of 3z plus 2, and this is equal to 3z plus 2 whole cube plus 1, and by simple calculation we get this equal to 27z cube plus 54z square plus 36z plus 9, where z lies in C. It is to be noted that if fz equal to u of xy plus I of vxy, then clearly conjugate of fz is equal to u of xy minus I of vxy, and f of z conjugate equal to u of x minus y plus I v of x minus y. From this we can conclude that in general conjugate of fz and f of z conjugate are distinct. Now we consider an example. Consider the function fz equal to 2 minus 3i into z. Find conjugate of fz and f of conjugate z. So here fz is equal to 2 minus 3i into z, and putting z equal to x plus iy, we get this equal to 2x plus 3y plus I into 2y minus 3x. Therefore, conjugate of fz is equal to 2x plus 3y minus I into 2y minus 3x, and by simple calculation we get this as 2 plus 3i into conjugate of z, and f of z conjugate, this is equal to 2x minus 3y minus I into 2y plus 3x, and this gives as equal to 2 minus 3i into conjugate of z. So from this we see also that conjugate of fz and f of z conjugate is not equal. So another example, so that the function fz equal to z square plus 2z plus 3 is univalent in the region mod z less than 1. Is the function univalent in the entire complex plane C? Give reason. So suppose that z1 and z2 be any two points in mod z less than 1, and f of z1 is equal to f of z2. Then obviously z1 square plus 2z1 plus 3 is equal to z2 square plus 2z2 plus 3. That is, we can write z1 square minus z2 square plus 2z1 minus 2z2 is equal to 0. That is, z1 minus z2 into z1 plus z2 plus 2 is equal to 0. So, from this we get Z1 minus Z2 equal to 0, that is Z1 is equal to Z2. Since Z1 plus Z2 plus 2 is not 0 in the region mod Z less than 1. Thus, f is 1 1 in mod Z less than 1, and hence f is univalent in this domain. We note that the function is not univalent in the entire complex plane C, because if we choose Z1 as 0 and Z2 as minus 2, then Z1 plus Z2 plus 2 is 0. So, f of Z1 equal to f of Z2 even though Z1 not equal to Z2. At the end of this module, we came to know some definitions along with 3 important theorem in complex analysis: Bolzano-Verstraete theorem, Jordan curve theorem, and Heine-Borel theorem. We also came to know the concept of functions of a complex variable, and we also discussed some examples related to this module. For more problems, you can see the self assessment part. You also consult reference books. This ends module 1 of chapter 2.